Hello, welcome back to MEC 975 Advanced Vibrations. In the last video, we began our discussion of the procedure of modal analysis, and we stopped right after mass orthonormalizing the mode shapes. In this video, we're going to continue that discussion, and we're going to begin by defining modal coordinates and the modal transformation, and then we're going to use that to decouple the equations of motion. So the modal transformation we're going to define is that x of t is equal to phi times eta of t. In this case, x is a vector, phi is our mass orthonormalized modal matrix, eta is the vector of modal displacements, which then implies that x dot of t must be equal to phi times eta dot. And why don't we let's drop both the function notation and the underbar notation. So this implies that x dot is equal to phi times eta dot, and x double dot is equal to phi times eta double dot. And this is known as the modal transformation. And that's because it represents a coordinate transformation from physical coordinates defined by the generalized coordinates of the system into a modal coordinate system. Okay, so what we're going to do now is we're going to substitute this modal transformation into the equation of motion. This will give, in the first case, we'll have m times phi times eta double dot plus, and at this point we're going to insert our proportional relationship for the damping matrix. So we'll have alpha m plus beta k, and then this is times phi times eta dot plus k times phi times eta is equal to ft. Next step is to pre-multiply by phi transpose. And this will give us phi transpose times m times phi times eta double dot plus, and let's bring the phi transpose on the inside. We'll get alpha times phi transpose m times phi plus beta times phi transpose k times phi, all of that times eta dot plus phi transpose k times phi times eta is equal to phi transpose times f of t. Okay. This term here, we said previously, due to the mass orthogonality relationships, we said that this must be an identity matrix. This is the benefit of mass orthonormalizing, that we get back an identity matrix rather than a diagonal matrix of modal masses. So again, here we'll get an identity matrix, and then here we get back a diagonal matrix with omega I squared in the diagonal terms. And then same thing here, we get omega I squared, or a diagonal matrix with terms of omega I squared And then this last term, we're going to call this n of t. And it represents the modal forces acting on the system. Okay. From there, we'll end up with I times eta double dot plus alpha I plus beta times the diagonal matrix with omega I squared in the diagonals. All of that multiplied by eta dot plus diagonal matrix with omega I squared along the diagonal times eta, and this is then equal to n of t. So n is a vector, I is a diagonal matrix with 1 down the entire diagonal, alpha I is still a diagonal matrix, beta times this is a diagonal matrix, this is also a diagonal matrix. So every term in this entire equation fits in a diagonal matrix, which means that the entire equation forms a diagonal matrix. And what that implies is that the equations are totally decoupled now. They no longer depend on each other. So the result of this is a set of n uncoupled equations. Set of n uncoupled equations, which we can write as eta I double dot plus quantity alpha plus beta times omega I squared, that times eta I dot plus omega I squared times eta I is equal to ni of t. Okay. From here, why don't we can do the following. Let's let zeta I, or actually let's let alpha plus beta times omega I squared, let's let this be equal to 2 zeta I times omega I. And then this leads to the relationship that zeta I is equal to alpha plus beta times omega I squared divided by 2 times omega I, or as it's commonly written, alpha over 2 omega I plus beta times omega I over 2. So from there we can then write that the modal equation is eta I double dot plus 2 zeta I omega I times eta I dot plus omega I squared eta I is equal to ni of t. So that's our modal equation. Let's now tackle the initial conditions. So for the initial conditions, we know that x of 0 is equal to u, but this must be equal to phi times eta of 0. And so in this case, this means that eta of 0 must be equal to phi inverse u. But because of the mass orthonormality or orthogonality condition, and because we're mass orthonormalized, this means that eta of 0 must be equal to phi transpose times m times u. And we can call this, we'll call this h. Similar thing can be done for x dot. So this will imply then that eta dot of 0 is equal to phi transpose m v, and we can call this g. Okay, great. So that leads to the final modal equations of and these are going to be eta I double dot plus 2 zeta I omega I times eta I dot plus omega I squared times eta I is equal to ni of t with the following initial conditions. Eta I 0 is equal to h, and then eta I dot of 0 is equal to g, we'll say. Let me move these down. There. There we go. Okay. This then leads into the fourth and final step. One thing actually before we do that, what I want to note here is that we've recovered a single second order ODE that governs the response of the ith mode. So we've created essentially a harmonic oscillator for the mode. In other words, this is the modal oscillator. Okay, the fourth step is really just to solve these equations, the decoupled equations for the modal displacements, and then we just perform modal superposition to form the final solution. Okay, so step 4 is to solve the decoupled equations of motion, or the decoupled equations, let's just say, for modal displacements. And these are the eta of t, and then we're going to perform a modal superposition. Perform modal superposition. To form the final solution. Which is x of t. Okay, so assuming that you can solve for these specifically from, well, you'll get a particular solution plus a general solution, or I forget the terminology, it's typically would be called the transient solution. Specifically, we can say that something like eta I of t is going to be equal to e to the minus zeta I times omega I t times cosine, we'll get in here x, well, first our initial conditions should have i's in them, and we'll get back something like hi times the cosine of omega sub d times t plus gi over omega d times sine of omega d t plus the particular solution, which depends on the forcing, and then omega d is going to be equal to omega I times the square root of 1 minus zeta I squared. So assuming you can solve for this, again this is particular solution, which depends on the forcing, so I can't actually solve for it here. Once you've solved for that, then simply you have that x of t is equal to phi times eta of t, which then leads to xi of t being equal, and this is the modal superposition. This here is modal superposition. And in terms of just for the xi coordinate, we'll get back that we have phi I, which is the ith component, phi I1, the ith component of the first mode, times eta 1 of t plus all the way up to phi I, which is the ith component of the ith mode, times eta I of t plus, and I need to move this a little bit over, plus up to phi I n times eta n of t. There we go. And that then is the final answer. That gives us our modal superposition. Both of these are the modal superposition. And this concludes our discussion of the procedure of modal analysis.